Hello everyone, welcome back, and I hope you're doing well, and I hope your preparation for your exams is also going well. So, in the last video, we had talked about the sample regression function, okay, and today we'll be continuing ahead. So, today we'll be talking about the problem of estimation. So, now we know what a sample regression function is, and through the help of a sample regression function, we'll try to estimate the population parameters. So we will get sample parameters, sample parameters, not parameters. Technically, I should cut this. We'll get sample statistic, and from this we'll try to estimate the population parameters. Right. Okay. So now comes the problem of estimation. Estimation. So this is the most important part here because the entire game is of estimation. Okay, so estimation becomes really important, and with the help of your sample regression function we'll try to estimate the population parameters. So our aim here is to estimate the PRF using SRF as accurately as possible. Okay, so how do we do it? We use, or we have two methods. So one is your ordinary ordinary least squares method. So we'll see what this method is in this video, and there is a another method which is called the maximum likelihood method. So we'll be sticking to this method only. This is not relevant to our syllabus. Okay, so we'll be talking about ordinary least squares method. Okay, so let's start the discussion. So we have the method of ordinary least squares. Okay, so let's talk about what this method is. Okay, so as we know, we have to derive the SRF, and through that we have to your estimate the PRF. Okay, and we know that from our previous discussion that yi is equal to yi hat plus ui hat. So from here I know that ui hat is equal to yi minus yi hat. Okay, and this can be written as yi equal to beta beta, sorry, let me rub this. So your ui hat can be written as yi minus beta 1 hat plus beta 2 hat xi. Okay, so this is something we know now. Okay, like we can derive this equation here with the help of our previous learnings. Okay, so what this method is about, how do we estimate our sample statistics using this method? So our aim is to estimate beta 1 hat and beta 2 hat. Our aim is to calculate these values, and with the help of these values we'll estimate our population parameters, which are beta 1 and beta 2. Okay, so we will have multiple such values. Okay, we'll take multiple such samples, the SRFs, we'll create multiple SRFs. Okay, and from there we'll get multiple these values, and from these values we'll try to estimate these values for the entire population. Okay, so what we try to do here is so as the name suggests, it says least squares. So we try to minimize the error term, sample error term. Okay, we'll try to minimize this error term while we create our sample. So whatever x values we choose or xi value we choose, so corresponding to those xi values, whatever yi values I get, I'll try to minimize the gap between the actual yi value and the yi hat value that I get for the sample regression function. So if I have an xi corresponding to it for the sample, I have a corresponding yi hat value, and then this will lead to a error term, sample error term. So there will be a gap. So this gap. So the actual yi will be a bit different from the yi hat that I get from the sample. So there will be a gap of your ui hat. So my aim is to minimize this gap. So as minimum this gap becomes, my sample regression function becomes closer to the population regression function. So this is the idea. So if this is the plot, okay, so there is this xi, say, so we have multiple values of y if this is the srf yi hat, okay, and there are multiple ui hat values here. So my aim is to minimize these values so that I can get a sample regression function that is closer to the population regression function. So this is what we'll work upon. So how do we do it? So one way is to minimize the sum of ui hat. So minimize the sum of ui hat. So I'll have some values of ui hat which will be far away from the function, the actual regression line, and there will be some values which will be closer to the regression line, and then there will be some values on the positive side and some on the negative side. So the problem with this minimization of the summation part of ui hat is that there are some negative values of ui and there are some positive values of ui. So overall, the term itself gets minimized on summation because negative and positive will cancel out. So this is not the best method because you know uh, this will not give me a real picture of how the values of yi hat are dispersed around the sample regression line. Okay, so if I sum the ui hats, they will cancel out and the remainder that I'll have will already be very small. So this might not be the best possible way to minimize my UI hats. Okay. So what is the other way? So in the other way round, what we actually do is, as the name also suggests, we minimize the squares squares of UI hat. So when I square the UI hat term, so whether it's negative or positive, the square is a positive term. So in real terms, I'm actually getting the differences, actual differences, or how dispersed the hat values are around the sample regression function or the sample regression line. Okay, so this gives me a real picture because uh, the actual effect is being captured here. So the only problem is that the square of uh, those uh, dispersion is being captured. So we have to square it because we have to take account for the negative UI hat values also. So that is the reason we are squaring it. Okay, because in the case of just simple summation, those values were getting cancelled out and the value was lower on its own, just on summation itself. So that was of no use to us. So this squaring helps us. So now what we do is we minimize the square square of ui hat square, which is equal to minus yi hat ka whole square. So we have to minimize this term. So how does minimization of ui hat square help us to get the values of beta 1 hat and beta 2 hat? So we'll see how. So if I write summation ui hat square is equal to summation yi minus yi hat square is equal to summation yi minus beta 1 hat minus beta 2 hat xi squared. So I can write yi hat as this term. Okay. So from this equation, I see that ui hat square is a function of beta 1 hat and beta 2 hat. Okay. This is very evident from this equation itself. So we will use this to find beta 1 hat and beta 2 hat for our sample regression model. The principle or the method of least squares chooses beta 1 hat and beta 2 hat in such a manner that for a given sample or set of data, summation of ui hat square is as small as possible. So we in this method try to choose our function, or we try to choose our beta 1 and beta 2 hat in such a manner that this summation or this error, square of the error around the regression line is minimized or it is as least as possible, and that is why it is called the method of least. Least least means we are minimizing this term, squares. So we have taken the square of the error term, so that is why this is called the method of ordinary least squares. Okay. So we have read in our mathematical economics part, or like everyone is aware of this principle, like when we have to minimize something, when to minimize a function, I differentiate the function with respect to a differential. Okay. And I equate it to 0. So this is the standard operating method. So in here we'll do the same thing. So we'll differentiate ui hat square with the partial differentials. First we'll take beta 1 hat. We'll differentiate ui hat square with respect to beta 1 hat, and in the second case we'll differentiate it with respect to beta 2 hat. So differentiating summation ui hat square with respect to beta 1 hat. So this gives summation yi minus beta 1 hat minus beta 2 hat xi. Okay. Which is equal to minus 2 summation ui hat. This is the first equation. So this term is basically your ui hat term. Okay. So that is being written over here. So this, on differentiating ui hat square with respect to beta 1 hat, I get this. Similarly, on differentiating summation ui hat square with respect to beta 2 hat, I get minus 2 summation yi minus beta 1 hat minus beta 2 hat xi, and here xi. So if I'll open the bracket, I'll get minus 2 summation ui hat xi. So this is my equation 2. So now we have two equations and we have two variables, right? So I have my beta 1 hat and beta 2 hat. So I'll use these two equations to find beta 1 and beta 2. So on solving, so I'm not doing the entire proof here. So on solving I, so if I put the first equation equal to 0, so I'll get summation yi is equal to n beta 1 hat minus beta 2 hat summation xi. So n is the number of values in the sample. This is my third equation, and similarly on putting the second equation equal to 0, I get summation yi xi equal to beta 1 hat summation xi plus beta 2 hat summation xi square. So I've just opened the bracket, and from there I've equated it to 0. So I get this. This is my equation 4. So on solving these equations, so these are also called your normal equations. So when I solve these two equations, I get beta 2 hat equal to n summation xi yi minus summation xi summation yi upon n summation xi square minus summation xi whole square, and which can be simplified to summation xi minus x bar upon y into yi minus y bar upon summation xi minus x bar whole square. Okay, so this turns out to be summation small xi yi small y. This is small y. I'll tell what small xi and small y represent here upon summation small xi whole square. Okay, so your x bar and y bar in the previous equation is simply your sample mean of x and y values, okay, that you have taken from the sample, and your xi is basically your xi minus x bar, and your yi is small yi is yi minus y bar. So this is how you get the value of beta 2 using the ordinary least square method. Okay, so that was the entire point. So we had to create a sample regression function, and from that function we had to get to beta 1 and beta 2 hat values. Okay, and using these values we'll try to estimate the population regression function or the population parameters. Okay, so this is your beta 2 hat. Similarly we'll also get your beta 1. So beta 1 hat is your, on solving those equations, I get summation xi square, this is xi, summation yi minus summation xi into summation xi yi. Okay, upon n summation xi square minus summation xi whole square, which is also equal to beta 1 hat equal to y bar minus beta 2 hat x bar. So the relation between beta 2 hat and beta 1 hat can be calculated through this equation. Okay, beta 2 hat. So I think this should be enough. I'm not exactly going into the proofs of all the equations because I think those can be clearly found anywhere. Okay, like if it's relevant for you to learn the proofs, I think you can check it from any standard book or any other website. So the important part was to explain the context and the way we estimate your population regression function, how beta 1 hat and beta 2 hat is calculated using your sample regression function, and how the ordinary least square method, which is to minimize the ui hat square values, is used to get your beta 1 hat and beta 2 hat values. Okay, so this was about your estimation problem, and this is all for this video. So in the next video we'll be talking about your classical linear regression model and their assumptions. Okay, I hope this there was some learning from this video. Take care and see you in the next video.